You may remember, and you probably don't remember honestly, that the definition of a Riemann integral says that we have to have a continuous function from some bounded region A to B, right? So what I would say is I want to integrate starting at 0, and I might go to 10, and the function that I integrate, it has to be continuous over that entire closed interval 0 to 10, right? If the function is continuous over 0 to 10, I can integrate it. That's the definition of how we did the Riemann sum and developed what we think of as the standard integral. So let's take a look at a specific example. Right, if I had something like 1 over x squared dx from 1 to 5, well, 1 over x squared, if I look at this function here, it goes to the point 1, 1, but it's continuous starting at positive numbers. It's not continuous at 0, but for any positive number, it's continuous. So clearly, from 1 to 5, it's continuous, no problem. So the Riemann sum, or the Riemann integral says, no problem. I can take the antiderivative, I can apply the fundamental theorem of calculus, I'm good. So I can do that, right? It's just simply negative 1 over x is the antiderivative by the power rule. If I take the limits here, I get, I'll plug in 5, and then I subtract when I plug in 1. And I can rewrite that as 1 minus 1/5, which is actually 4/5. Okay, great. Right, hopefully you could have done that without me. So then what happens if I say 1 to 10? Okay, well it's clearly continuous on 1 to 10. I get 9/10. Now if I go all the way out to 100, it's 99 100ths. But what if I keep going? What if I say, all right, you know what? I want to take this thing all the way to infinity and see what happens. What happens if I don't just integrate, I don't stop, I just keep on going? Well, you might be able to guess. I go 4/5, 0.9, 0.99. If you did it out to 1,000, it'd be 0.999. And we're getting closer and closer to something. And notice that it's 1 minus something, and that denominator is related to that limit of integration. So when I set up something that looks like this, now I have an infinity as one of my limits of integration. Well, that's kind of odd, right? That's not a very typical thing to have. So what we do is, this is really a shorthand. When you see something like this, it's called an improper integral. And the reason it's called an improper integral is that by definition of the way a Riemann integral works, this is not defined. This is not a well-defined statement. So it's considered improper, because the proper way to write that is something that looks like this. You take 1 to an arbitrary number and you take the limit of that number. So you sort of think of the integral really like a function, and you want to take the limit of that function out to positive infinity. And it's a perfectly reasonable and an okay thing to do in calculus, because all that calculus is doing is developing a series of rules about how functions behave and how they interwork with each other. And once we've satisfied those rules, we can apply the components we have. So we have the pieces here, we have a limit, and we have something by the fundamental theorem of calculus. This is the antiderivative big F at B minus big F at 1. Well, big F at 1, that's just that's a constant, right? So we don't have to take a limit of that. But then we take the limit of big F at B. So really what we're trying to ask ourselves when we think about improper integrals, don't think about the pieces, don't think about the components, don't think about any of that stuff. We're really trying to figure out, is this thing going to blow up on me? Because if I'm taking this integral, I can see that it's positive the whole time. So I'm going to keep adding a positive number, and another positive number, and another positive number, right? I'm adding up that area under the curve. Well, if it's always positive, why wouldn't it continue to add up to infinity? Why wouldn't it just blow out and say, that's just goes off to infinity? And the answer to that is that essentially what happens is that this thing shrinks so quickly, it shrinks so quickly that when we add up those little pieces of area, all we get is crumbles, all we get is dust. We don't get enough to make a substantial mound that builds all the way up to infinity. We lose it too quickly. It goes through our hands. And that's the idea here. Notice that if I were to do this, I get 1 minus this 1 over b. Well, as I take b to infinity, that limit just shrinks away, right? It just vanishes. And all we're left is that the area under the curve, starting from 1 to infinity, that area is actually 1, which is a very small number if you think about that. But anyway, that's the idea behind an improper integral. Improper integrals have a lot of value in actual practice. What you can do is, if you want to set up what the long-term behavior of something is, you can say, all right, well, I expect for this thing to gain at this rate. And I really want to determine if it's stable. If I take it out to infinity, is it going to blow up on me, or is it going to kind of level out? Another huge thing is, and we'll get there as time goes on, is this idea of what's called the integral test for convergence. And this has a lot of relationship to real life, because you can set up these things where you keep adding sums, like those sigma sums, like we did with Riemann sums. And if you just keep adding and adding and adding, how do I know if it adds to infinity or converges? And you can relate it to an improper integral. So that's a little bit of just extra flavor there. But the idea behind this is that this is a very powerful piece of mathematics. Now, in terms of integrals, there's really 3 basic cases that you deal with. And it's considered, we do this and it's considered improper if, really the first case is that if it's not continuous on the interval. So what this means is that it doesn't actually matter if if one of these things is infinity. It doesn't matter if one of those things is infinity. If it just stops being continuous on an interval, then the standard Riemann integral does not define that very well. So think about something with what's called a jump discontinuity. If I have sort of think of a light switch function where it's just off and then on, off and on, right? So it goes from 0 to 1. Again, think like you're turning on a light switch, 0 to 1. If I wanted to integrate something that looks like that, that's improper, because it can't be discontinuous. So we have to break it up in a very specific way. So that's a very common improper integral. Then the next thing is, and this is actually probably the most common, is that f becomes unbounded. So for instance, if I wanted to take the integral not from 1 to infinity, but in the case here, if I want to go from 0 to 1, well, the problem is that this function just keeps on shooting off to positive infinity. It's not defined at 0, so it just becomes unbounded, just goes away. And it might go down to negative infinity or whatever. So you might have to ask yourself, okay, is that thing running away so quickly that it's actually going to shoot the integral off to infinity, or even though it's shooting off to infinity, are those horizontal strips so thin that it doesn't actually make the area shoot off to infinity? It's a really interesting idea. And then the final, and these are the easiest to spot cases, where either your lower bound is negative infinity or upper bound is positive infinity, right? Those are easy. If I see something that looks like this, I know it's improper. I don't have to think about it. I don't have to worry about it at all. If either one of those things has an infinity in it, it's over. It's over. It doesn't matter. And sometimes you'll have both, because you want to integrate over every possible value. Really good examples of this are in statistics. In statistics, what we might want to consider is all the possibilities of input. Well, if literally any number is possible, now it might be very, very improbable, but it's still possible, then when you find your cumulative probabilities, you have to go all the way out to negative and positive infinity. So there are actual practical use cases for things like this in other mathematics courses and in sort of real-world applications. But anyway, we're going to get to these, and we're going to do some examples of these, but really these are the 3 pieces, and we're going to talk about how to set those up and how to solve for them.